Okay, welcome back. So we're going to do a couple of problems with the and or statements. So let's start here. In fact, I'm going to grab this example from the book here. Not that one, this one. Let's take x is greater than negative 2. And let's start with and. Let's just do an and statement, and then I'll do the same problem in an or statement. And x is less than 4. So again, if I just kind of draw out pictorially what's happening here, my x is greater than negative 2, gives me a negative 2, open circle, and shade to the right. X is less than 4, gives me an open circle at 4, and shades to the left. Right? For this problem, I'm looking for the and, or the intersection. And you can see that that intersection happens right here in the middle. None of these guys are in there because they're not in the second group. None of these guys are in there because they're not in the first group. And so it's just the numbers between negative 2 and 4. But I don't include negative 2 or 4 because negative 2 isn't included in the top group and negative 4 isn't included in the bottom group, so they can't be in the intersection. And so my final answer here is that the solution to the and compound inequality is negative 2 to negative 4. Or excuse me, negative 2 to 4. Right. Let's take a look at this as a or statement. And I don't have to change a lot. My answer is going to change, but I don't have to change a ton. If I look at this as an or statement, now it doesn't matter that these guys weren't part of the top group. They're part of the bottom group, so they're in. It also doesn't matter that these guys weren't part of the bottom group. They're part of the top group, so they're in. And so it's all of the numbers between negative infinity, forever that way, all the way up to 4, but also all of these guys. And so if I kind of push these together in a union, it's everything. Every single number is either on the bottom or the top or both, right? And so with my or, this is the union. We can pictorially see that this is simply negative infinity to infinity, or another way of writing that is just simply the double barred R. Now, of course, this is a very simple example. I didn't have to do any math to get to this point. Sometimes I might have to. So let's take a look at a problem where I have to manipulate in order to get to this point. So if I have, let's say, 2 times x plus 1 plus 5 is less than or equal to, let's go 7. Okay. Or, let's say 3x minus 5 is greater than or equal to, say 4. So I've got two inequalities. They're conjoined with an or. It's a compound inequality, right? I have to satisfy the or of these, so I have to figure out the solutions to one, I have to figure out the solutions to the others, and then figure out what the union of those two are. So I'll start here. I can distribute. This becomes 2x plus 2 plus 5. Combining like terms here gives me a 7, so I've got 2x plus 7 is less than or equal to 7. I can subtract my 7. Remember that your addition principle is guaranteed, it's given to you, whereas you just have to be careful when you multiply or divide by negatives here. But we're not going to. I end up with 2x is less than or equal to 0. If I divide each side by 2, I get x is less than or equal to 0. That's 1. Solving the other one over here, again I go through the same motions. I'm going to add 5 to both sides. That gives me 3x is greater than or equal to 9. And then I just divide each side by 3. And I get x is greater than or equal to 3. Right? So those are my two sets. All of the numbers less than or equal to 0, all of the numbers greater than or equal to 3. Right? And if I draw this out, right, I've got, this will say is x is greater than, less than or equal to 0, is just simply at 0, a closed circle, because it's the inclusive less than, and then everything to the left. Right? But x is greater than 3, greater than or equal to 3, is at 3, a closed circle, and shade everything to the right. Right? It's an OR statement, so it's a union. It's the union of these two sets, and therefore it's negative infinity up to 0, including 0. There's a break, right? There's some numbers between here that aren't included, so that's a union. And then again, that other set from 3 to infinity. And that's that. And I think you should be able to realize, well, what would happen if this were an AND? Then you'd have the intersection, and there is no intersection, so if this was an AND instead of an OR, we would have the empty set, or nothing, as our answer. Okay. All right, good. Then the last thing that we want to look at here is these tripartites. There we go. I believe I mentioned this in an earlier video, and I forgot what they were called, and then I probably remembered in the next video after that, but a tripartite is a way of writing a compound inequality in just one line instead of an equality with a conjunction with another inequality, right? So let me show you what I mean here. This tripartite, there's 3 parts. That's what that word means, right? There's 3 parts of it, but there's really 2 expressions happening here. If I ignore the right-hand side inequality, I get -4 is less than x, which is the same thing as saying x is greater than -4, right? A lot of times it's hard to read math backwards, but if you read this from right to left, this is the same thing that you get. It looks like I wrote it backwards, but that's all right. I also have the right-hand inequality. If I ignore the left one, I get x is less than 10, right? When you see a tripartite in this form, this will always be an AND statement. Okay? So this means literally, this, I'm going to write this one backwards, but x is greater than -4 is my first inequality, and x is less than 10. Right? Which is, you can typically then say, well, x is then basically sandwiched between the left and the right. So if I wanted to write this in interval notation, it's pretty quick and easy. It's just between -4 and 10. Parentheses, because these are strict inequalities. And if you draw these out, you'll come to the same conclusion that you should be between -4 and 10. All right, let's work with one of those because they can get a little bit ugly. I think there's a good example in here. Yeah, the very last example. Says we have 9 is greater than -2x plus 5, which is in turn greater than -13. And typically you'll see these inequality signs, they should be going the same way because we should be sandwiching something between 2 numbers if one is less than and the other one's greater than, it was written wrong. You shouldn't see it that way. It's not guaranteed to work out very well. But in this case, they're pointed the other way. We're going to end up pointing them back the other way when we get rid of this negative. But I have three parts, and essentially I have these two inequalities that I'm working with all simultaneously. And so if I use the addition principle, let's say to isolate the x in the middle, which is what we want to do, I'm going to start by subtracting 5. And if I were just working with this equation, that was an inequality, I would subtract 5 from both sides. If I were working on this inequality, I would subtract 5 on both sides. And so I might as well just work on both inequalities at the same time and subtract 5 everywhere. And I can do that. As long as I subtract to all three places, then it's legal, right? So 9 minus 5, that's a 4. Still greater than negative 2x. Still greater than negative 18. And I can get rid of this x completely alone by dividing everything by negative 2. Now when I do that, if I ignore the right hand, dividing by negative 2 is going to flip this sign to be a less than. And if I forget the left hand side, dividing by negative 2 over here is going to flip this one to be less than, right? 4 divided by 2 is negative 2. Negative 2 and negative 2 cancel out here, leaving me with the x. That's what I want, is the x all isolated in the middle, and then 9. And so I found my solution. X are the numbers between negative 2 and 9, or in interval notation, that. All right. Hopefully that was helpful. That was the end of this section. I'll catch you on the next one.